live now. Give me 1 second. Just need to mute here on the, otherwise you'll hear it twice.
Hallo, hier Jen. Oh, lieber Matthias. Welcome.
Hey, surprise.
Yeah.
It's all good. I think, not sure if it's, no, not yet. And yet. All right. Let's start sharing of this. You see things there, right? Okay. Okay, thank you. So let me start. Now we are all here. I would like to, welcome you all back again to the online SPICE-SPIN+X seminar series. As you know, it's in a Zoom webinar format, so that most of the participants will all be able to see it. Several 100 or so, or 150 participants can only see the speaker speaking, but please write down in the, I think maybe the chat is available, but also particularly the Q&A, any questions you may have, or raise your hands afterwards, and I will give you the floor or promote you to panelists to be able to ask directly to the speaker our questions. And please check out the next few sessions that we have. We are all scheduled up to May already. And please suggest any speakers, of course, if you have any suggestions. As you know, the SPIN+X seminar series, the SPICE seminar series, is done by myself and the University now in Duisburg, and in collaboration with the SPIN+X Collaborative Research Center led by Martin Schliemann, Burkhard Hillebrand in Kaiserslautern, and Matthias Chloe in Mainz. Today is actually a pleasure to go a little more up. I don't know what happened. 1 second. To introduce Matthias Weiler, who joined, unfortunately during COVID time almost, Kaiserslautern, and he's the head of the group of applied spin phenomena at Kaiserslautern. And he had a very successful time in Munich, also PhD in Munich, and then is very well known in the community by spintronics and magnonics, and particularly controlling the dynamics through light, sound, temperature, and many other effects in this fascinating field of magnonics. He has several awards. One of them to highlight here is the award given by Munich in 2019, the Supervisory Award, and the Schofers Foundation Dissertation Prize Award. So with this, I will ask you, I'll stop sharing and ask you please to go ahead and share your talk and start whenever you like, Matthias.
Okay, Jairo, thanks a lot. So thank you a lot for the kind introduction, and of course also thank you a lot for inviting me to give me the opportunity to show some work that we have been doing in the past, well, decade basically, on the topic of magnetoacoustic waves. Also, thank you for the wine that I got for giving the talk here. So that's a great pleasure. And it's almost a good substitute for meeting in person and going for dinner, which we'll hopefully be able to do as well in the near future. So before I begin, I have several acknowledgements. First of all, it's all the funding agencies that you see here on this screen. And then also, most importantly, all those people who have contributed to the data and to the experiments that I'm going to show you today. And there is, first of all, the groups of Burkhard and my group in Kaiserslautern who have been working on these magnetoacoustics, as well as all the work dating back to my time at the Walter Meissner Institute and TU Munich, and now a very active collaboration, which is going to be the main part of this talk with the University of Augsburg. And also at the very end of the talk, I will show some very recent results that have been achieved in collaboration with IMEC and IMT in Bucharest. So with that, let me get started. And I want to start with giving a brief outline of the following 45 minutes or so. So because this is more like a general audience and not everybody is probably familiar with magnetoacoustics, I will start with like an introduction, also more of a historical introduction about magnetoacoustic waves. After that, I will then dive into the actual physics and the current results. And there is four things I want to highlight in this talk. And the first one is I'm going to show you the symmetry of the magnetoacoustic interaction, as well as the origin. And then finally, I'll go on to non-reciprocal phenomena that can be observed in magnetoacoustics and nonlinear phenomena. So let me get started with the introduction. So I guess in this community of SPIN+X, everybody is familiar with spin waves. So spin waves are excitations of magnetically ordered systems, and they have found applications in data processing. So it is well established by now that one can build so-called Magnon logic. So one can, for instance, build magnetic logic gates, as shown exemplarily here, which uses the interference and the control of spin waves to implement logic elements with a potentially much smaller footprint and lower energy consumption than possible using like a traditional CMOS-based network of transistors. On the other hand, there's also sound waves that are very actively used in present-day applications. And every one of us carries around dozens of these sound wave devices all the time. And that is because they are used in our mobile communication devices as acoustic filters. So these acoustic filters, I will go into some more details later. Well, they have a very small footprint, so about 2 millimeters squared here. And still, despite a small footprint, they have a very good filter performance. And there is a typical example shown here on the graph on the right for some filter that is used for GPS antenna in your mobile phone. And well, it has a performance of an insertion loss of 1 to 2 dB, and it has an out-of-band rejection, which is better than 50 dB. Okay? And that is something which you would do, if you would want to achieve it without using acoustic waves, it would require a much larger and much less efficient device. And that's why this is actually a big market, so 5 billion market roughly now in these filters here. And now the general idea of this magnetoacoustics is, well, if we have these two separate, very successful projects going on, why not combine the advantages? And what we can do if we combine magnetic and acoustic waves is there's two main things, and one of them is we could potentially miniaturize non-reciprocal microwave devices, because such devices are nowadays typically based on combining microwave photons with magnons. And because those photons have rather large wavelengths at the typical gigahertz frequencies, we end up with rather large devices, so centimeter scale. If you could instead do it using phonons at the same frequency, one could envisage that these devices could potentially be downscaled by orders of magnitude. And the second is because the phonons, again, have a very comparable wavelengths to the magnons. So here's typical schematic dispersions of photons, the magnons, and the phonons shown. It should be a great way to actually control magnons. So for instance, doing things like parametric pumping, which is very well established with photons at k = 0, so for Bose-Einstein condensates, for instance. But doing that and using phonons, so actually pumping at a non-zero k vector. So well, this entire combination of sound and spin is by no means a new idea. So it dates back to around the 1960s when actually Charles Kittel wrote down in a theoretical proposal that this should be useful to generate spin waves from elastic interactions. And the magnetoelastic interaction that was considered there is fundamentally based on a spin-orbit interaction, and it can be phenomenologically described by the magnetoelastic free energy density, which is shown here, which has combinations from pure strains. So these are these epsilons over here, and shear strains the epsilons with this kind of like combined indices. And in this original work by Kittel, he only considered these two shear strain components, which are actually proportional to the mz component, where z is the component along the static magnetic field, along the equilibrium orientation, just as the largest component. And if one does follow this idea, one can then calculate a magnetoelastic field, which is just the gradient of this free energy density with respect to the magnetization directions. One observes, okay, we get this magnetoelastic field shown here in x and y components. And because the epsilon strain is an AC strain, it's modulated in time, we can get a modulated magnetic field. And the strength of this magnetic field can also be estimated. So one can take a typical magnetoelastic constant, which is about 10 Tesla in most materials, typical strains that are easily achievable in the order of 10 to the minus 3, and then one obtains a magnetoelastic field of about 10 millitesla, which is quite a substantial field. And that should then, we should then be able to use that to control dynamics. Experimentally, even very shortly after this proposition by Kittel, it was shown experimentally that this interaction exists. So there's this experiment by Bömmel and Dransfeld, who used two microwave cavities that were combined with a quartz rod, so piezoelectric material. And on one side, there was a thin film of a ferromagnetic metal, so nickel in this case. And what they did is they excited the ferromagnetic resonance in the left-hand cavity, where the nickel was in the antinode of the magnetic field of the cavity, and then measured the output on the other cavity, where the quartz rod was in the antinode of the electric field of the cavity. And the data is shown here. So they showed that from FMR, one can excite a sound wave via magnetoelastic coupling that generates an electric field, and that is something we can detect again. More modern approaches of these magnetoacoustics, they use surface acoustic waves. And surface acoustic waves are well known in two domains. Well, on the macro scale, these are earthquake waves. And in the micro scale, these are exactly the type of acoustic phonons that are used in our mobile phones for frequency filters. And there the typical device looks as shown here. So we typically have two so-called interdigital transducers. So those are transducers that are used to convert the microwave frequency electric field that is applied to them to a phonon, or vice versa, convert the phonon back to the microwave frequency, and they exploit the piezoelectric effect as schematically shown here. And then going to the magnetoacoustics, it's in principle very simple, because all we have to do is we have to deposit a magnetic thin film in the propagation path of the acoustic wave as shown here on the right-hand side. And then we have a spin wave in this greenish material, which should be the ferromagnet. It can interact with the sound wave flowing here, and it will be accompanied by an electric field, because the yellow material here is piezoelectric. So based on that general idea, early experiments started around 1976 using these surface acoustic wave devices. And they used a rather low frequency of the acoustic of the surface acoustic wave of about 100 megahertz, which is far below the ferromagnetic resonance frequency of, at that time, it was a nickel film. But nevertheless, what one sees is the so-called delta E effect, which means that the elastic moduli of a material, of a magnetic material, depend on its magnetization direction. And in the data, they used a nickel film that had a perpendicular magnetic anisotropy. So with zero magnetic field, the magnetization points out of plane, large magnetic field, the magnetization points in plane, and at some intermediate magnetic field, you get some tilted magnetization. And they actually observed that this will lead to a change of the acoustic velocity, which they attributed to this delta E effect. So that was the first surface acoustic wave plus ferromagnet interaction experiment. Later on, the frequency was a bit increased, so now about 600 megahertz, so almost in the regime where one could excite FMR. But then these authors here, network, they used an in-plane external magnetic field, an in-plane magnetized nickel, And what they observed was the following data for the attenuation of the acoustic wave. So some hysteretic behavior that then could be traced back to an AC susceptibility. So basically what these authors showed is that, well, indeed, the acoustic wave generates a virtual magnetic field as suggested by Kittel all along. That virtual magnetic field just works like the Tickle field that is used in an AC susceptibility measurement. And that's why the measurement data here looks basically identical to an AC susceptibility measurement of one and the same sample. And then several years later, we used basically the same experimental setup, slightly higher frequencies, so now in the gigahertz frequency range. But we now looked at the case where we're actually matching the ferromagnetic resonance frequency. And what we observed is, depending on the frequency of the acoustic wave, we observe for a little and then more absorption. And now we see non-hysteretic absorption peaks or transmission minima in the acoustic wave propagation. And the curious thing about that is it will depend in a very characteristic manner on the direction of the externally applied magnetic field with respect to the axis of the acoustic wave propagation. So here on the right-hand side, so they've shown our measurement data, where like the black signifies an enhanced absorption, and the white means there is little to no absorption of the acoustic wave. So we observe this characteristic fourfold symmetry in the absorption of the acoustic wave. And exactly that symmetry, that is going to be the first real thing that I want to discuss here. So why do we actually observe this characteristic symmetry? Because the FMR frequency itself in this nickel material that we had doesn't really strongly depend on the in-plane orientation of the magnetic field. Okay, so that brings me to the first part after the introduction here, and that's the symmetry of this interaction. So to understand the symmetry, we go back to the model by Charles Kittel. So here I will only selectively chose 3 different strain components. There's a reason why I chose those. It will become evident in the next few slides. In general, we can add all of those. So we have these magnetoelastic free energy density, and each of these strain components here could then be identified with some strain component that one gets in the acoustic surface wave. We can generate or we can calculate virtual magnetoelastic fields, right, by taking the derivative of this free energy density with respect to the magnetization orientation mx, my, mz. Okay. And when you do so, so you calculate the simple derivative, and then you have to consider that to actually exert a torque on the magnetic moment m. Of course, you need to have a component where this cross product here does not vanish. And if one also considers this cross product, one can then calculate where we get the maximum torque on the magnetization, and that's shown here on the right-hand side. So these blue lines or these blue curves here, they show what direction of the magnetization gives the maximum torque. And for a simple compressional wave propagating along the x direction, it's always the coordinate system here, one can see that the optimal angle for exciting magnetoacoustics is a magnetization direction of 45 degrees, meaning in plane in between the x and the y axis. One can do exactly the same consideration. What happens if you rotate the magnetic field out of plane? Also there you see the 45 degree angle. We can then also do that for other strain components. Here, for instance, for a in-plane shear strain, so for an acoustic wave that propagates like that. And then you can see, well, now we would expect maximum efficiency for the magnetoacoustic interaction at 0 and 90 degrees. And then on the other hand, for another shear strain, it would actually be not fourfold, but only a twofold symmetry that should be observed. Okay, so that means the symmetry of this acoustic interaction will depend on the strain components that we have in the phonon or in the acoustic wave. For instance, if one says we have a typical Rayleigh wave, so prototypical surface acoustic wave mode, which is dominantly a pure wave along the x direction, so pure compressional acoustic wave, you would actually expect such a fourfold symmetry. And that's exactly what we see in the experiment, where the deviations from this very simple model to the experiment are mainly due to magnetic anisotropy, which means that the angle of the magnetization is not always following the angle of the external magnetic field. Okay, so that is something that we understand very well, that this should be the symmetry. And well, it took a while until we then realized that this could really be exploited also experimentally to change the symmetry. And what we did is we used a piezoelectric substrate, which is a lithium tantalate, and that material is known to support two different types of surface waves. And one is the traditional Rayleigh wave, as in all these animations that I showed you before, which means it's a combination of a compressional wave mainly and like a shear wave in like this direction. And the second mode is the so-called in-plane shear wave, which means that it is kind of like having an in-plane shear displacement while it propagates. And these two different modes, they have different acoustic group velocities. One of them is more around 4,000 meters per second. The Rayleigh mode is more around 3,000 meters per second. And because they have different velocities, we can separate them. So what we can do is we can measure the transmission from one IDT to the other. So that's our S21. And we can then use the measured data that we measure in the frequency domain. And we can do an inverse Fourier transformation to the time domain. And that's the data that is shown here. And what we observe in the time domain is, well, there are several peaks of the transmission. The first one happens like immediately at t equals 0, more or less. And that is an electromagnetic crosstalk between these two interdigital transducers. So that's a photon. Okay, so we're not interested in that. Then there is some other peaks over here, and I will come back to those small other peaks in a second. And then there is like one peak over here. And that from matching the expected group velocity, we know this should be a shear wave mode. And then there is another peak over here, and that should correspond to a Rayleigh mode. Can change the frequency a bit. I mean, we have IDTs, transducers here with a relatively high bandwidth, so we can perform these experiments also at slightly different frequencies and still excite the same modes, basically. Okay, so if you look at that, we can then, using our time domain analysis, analyze the magnetic field dependence of this acoustic mode here. It should be a shear horizontal mode, right, as shown schematically here. And if one does that, we observe in experiment and also in our corresponding model calculations or corresponding fit even here, that we indeed observe such a symmetry where the magnetoacoustic interaction is maximized if we have an external, if we have a magnetization aligned either along the propagation direction of the acoustic wave or orthogonal. And maybe more for the magnonic experts, that means this particular shear horizontal wave can couple very efficiently either to Damon-Eschbach or backward volume spindles, which I think makes it very interesting for magnonics. On the other hand, if you look at the Rayleigh wave, which appears a bit later by doing this time domain analysis, we can see that we recover this traditional fourfold symmetry that we would expect for a Rayleigh wave. This is one and the same sample, same frequency, just looking at different times. Now there's many more peaks that I have not talked about so far, and we can also look at these other peaks. So as it turns out, most of these other peaks, so for instance, this one here and that one here, they will not show any magnetic field dependence. And they can then be attributed to bulk waves. So these are bulk acoustic waves, and they simply do not propagate through the magnetic material. So there's no magnetic field dependence in their transmission. Well, it's true for all these peaks shown here, other than this kind of like, well, unassuming small one over here, which is marked here in gray. And we can also look at the transmission at this particular point in time, and again perform our same data analysis procedure, and then we can see that the symmetry actually matches exactly that of the shear horizontal wave. So that means we observed a mode which we did not find in finite element modeling using COMSOL. So it was kind of like a surprise for us that it was there. So it's an unknown surface acoustic mode, at least for us. We could not figure out what it is, but we do know that it is a shear horizontal mode. Right? And that is something which is typically not so easy to do using other measurement means. But here with the Magneto-Acoustic interaction, it's actually very, very clear which strain components are observed. So this could be a powerful tool, even analyzing surface acoustic waves, some surface acoustic wave symmetries on substrates that might be more complicated than lithium tantalite. Okay, so that's the symmetry of the Magneto-Acoustic interaction. And next part is the origin. So at the very beginning, I already talked about Charles Kittel. And you might think, well, this is trivial. This is just magnetoelasticity, right? So it's been known for hundreds of years. Well, and I'm going to say it's not quite so simple. Okay? So we started looking at this origin of the Magneto-Acoustic interaction using a system which we thought would be very simple. So we used a Rayleigh wave on lithium niobate material on the frequency of about 7 gigahertz of our surface acoustic wave. And we looked at a simple cobalt iron boron film with a thickness of 2 nanometers, which is here indicated by this gray blob here. Okay. If one looks at the data, well, one sees that there is some, non-reciprocity in the transmission. Right? So we can measure, or we can invert the direction of the acoustic wave. So that's the red and the blue curve, corresponding to acoustic wave propagating in that direction or in that direction. And you can see that the absorption here on resonance, so on hitting the spin wave resonance, is actually depending on the acoustic wave propagation direction. Okay. So question that we ask ourselves, well, why is it non-reciprocal? Does that mean that these magnetoacoustic waves are actually chiral? So one can start with simple model again, what we would expect. So we would expect if we have a Rayleigh wave, so you have like the displacement of each lattice atom is shown here on the top, describes such an elliptical trajectory on the surface. While using these displacements, so these are the displacements ux and uz, forgot to add the coordinate system here, you can calculate the strains. Right? And then using the standard magnetoelastic approach from Kittel, we can write down what are the corresponding virtual magnetoelastic driving fields. So we would expect, well, if we have both strain components, if we have a strain component of a shear, so it's like an out-of-plane shear wave and this compressional wave over here, we should in generally expect to see an elliptically polarized driving field. And it's really elliptically polarized because you can see it from this animation. This component of the compressive strain and this shear strain, they're out of phase by 90 degrees. Okay? So that can be translated in really having like a virtual driving field which rotates. Okay? And that hence means it has a sense of rotation. Right? So here we have the sense of rotation counterclockwise of the atoms. Right? And you could imagine, well, if that matches the sense of the oscillation of the magnetization, then when hitting the resonance condition, you get a strong coupling or a strong absorption of the acoustic wave. And if you invert the direction of propagation of the acoustic wave, of course, all the atoms will move in the opposite helicity. So here, clockwise now, that should then also mean that the driving field is now rotating and here in the clockwise direction, not counterclockwise anymore. And that should then result in poor coupling to magnetization dynamics. Okay? And that, well, should explain our non-reciprocity. So at that point, one could think, well, the case is closed, right? Magnetoelasticity explains everything. Well, it turns out if one looks in the literature, on a paper here, Sadamichi Maekawa and co-workers, who showed that, well, indeed, in a thin film limit, and with a 2 nanometer thick film, we are in the thin film limit. At the surface, so really at the surface of this surface acoustic wave here, actually the shear strain vanishes. So you should really expect to get a purely linearly polarized driving field. And that should in no way be non-reciprocal or chiral. Well, however, it turns out what does not vanish is the rotation of the lattice, so the displacement. And the displacement that can, or that actually means that what really happens is if you have this film and you have this wave, basically the film normal, which is an anisotropy axis, right? So it's the anisotropy just from the demagnetizing field of the film. It's actually modulated, right? Because the anisotropy axis will always be normal to this film here. And that's called the Magneto Rotation. And the Magneto Rotation is, I think, a kind of like interesting addition to magnetoelasticity because it actually does not require any magnetoelastic medium. Right? It's just really the mechanical rotation of the lattice and the strength of the anisotropy here written as the effective magnetization that causes this virtual driving field. Okay, so now we have these two different possibilities for getting a elliptically polarized driving field. So we can either have magnetoelasticity, so when this B, which is the magnetoelastic constant, is not zero and this epsilon xz is not zero, or we can get magnetorotation if the M effective is not zero and well, this rotation of the lattice is not zero. But unfortunately, they both have exactly the same symmetry. They both depend on cosine phi, where phi is the angle between the magnetization and the surface acoustic wave propagation direction. So there's no easy way to disentangle these two contributions. So some time ago, the group of Otani showed that, well, indeed, if we look at such a cobalt iron film, so it's here 1.6 nanometers, we get a strong non-reciprocity of the acoustic wave propagation. And they argued that because, well, there cannot be any magnetoelasticity on the surface, this has to come from Magneto rotation, right? And it looks very similar to the data that we observe in a very, very similar material system. Well, we wanted to know that in a bit more detail. Is it true that you only get Magneto rotation coupling in thin films, or is there also still a contribution due to magnetoelasticity? And in order to resolve that, one has to actually go to finite element modeling. So that's what we did. We used COMSOL multiphysics to model the strains we get from a Rayleigh wave here in this case. So we used the lithium niobate substrate and excited using the piezoelectricity of the lithium niobate, the Rayleigh wave. And then from the simulation or from the finite element modeling, we get the strain components as a function of the z coordinate, which is basically going from z equals 0 at the surface to negative c into the bulk of the material. And here one can see, well, indeed, if you look at the shear strain component and we look at it as a function of the z coordinate, at the surface, it actually really goes to 0 as expected. Right? So there should not be any magnetoelastic coupling. However, if one adds into the simulation the magnetic thin film, even if it is only 2 nanometers and it has some cap layer, different materials, MgO or platinum, that could be used for capping it, then one actually finds, well, in the magnetic layer, there is still a, well, non-zero, well, small but non-zero strain component. Meaning, well, the situation is really complicated, right? So you cannot safely assume that there is no magnetoelastic coupling at all. Okay. So what we did is we developed a full quantitative and fully analytical model that should allow us to separate between the magnetoelasticity and the Magneto rotation. And to that end, we used from the finite element modeling, we got these strain components, the epsilon xx, the epsilon xz. We took the magnetoelastic constants B1 and B2 from literature, and we know that the displacement here at the surface, so the UZ0, is related to the acoustic power applied to the surface acoustic wave. And K here is the K vector of the acoustic wave. We can then calculate the expected driving field, right? And that's shown over here. So that's the expected magnetoelastic driving field, right? So these symmetries appear again here. And we model it as just being a plane wave which has the wavelengths corresponding to the wavelengths of the acoustic wave. We can then calculate analytically what is the expected power absorption, so how much of the acoustic power is absorbed as the surface acoustic wave propagates through the film. And by solving a differential equation, we ended up with this expression over here. P0 is the input power, and C is a constant here that depends on the volume of the ferromagnetic material, and the wave vector, and R and W are some geometrical constants. So, of course, the absorbed power comes from a excitation of spin dynamics, right, of spin waves. So what enters here is the pole susceptibility chi. And well, the nice thing about it is you can really be creative and put into the chi whatever you like or whatever you think you need. And we went kind of like all in here and put all the contributions in there that we could think of. So we put in some dipolar interactions, so this term with G0 over here. We put in the exchange spin wave over here, the term with K squared. We put in an in-plane anisotropy. We put in an out-of-plane anisotropy. We put in the damping. We put in Chalazhinsky-Maria interaction. Okay, so it was kind of like just everything that came to our mind. Okay, and well, then we use this model, so this absorbed power, because this is what we measure, and then we can actually fit it, right? We can then introduce any number of parameters here as fit parameters, fix some of the parameters from broadband ferromagnetic resonance spectroscopy measurements, like, for instance, the alpha. Okay, so quantitative modeling of such data is what we can then do. Do the quantitative modeling, and we fit our data. You can see here on the top row is the experiment, the bottom row is the corresponding fit to our model. You can see that the agreement is excellent, right? So there's no way to tell which is the data and which is the model without knowing it. And we can then, from that, extract the fit parameters, which are mainly these effective magnetic fields BXX and BXZ. We can do that for different samples. So we did it here for a sample series where we varied the thickness of the cobalt-iron boron and had some, I think, 2 nanometers of platinum on top. And what we observe is that, well, while the pure strain is pretty much independent of the thickness of the cobalt-iron boron, this component coming from the shear strain or from the Magneto rotation, for that matter, is actually somehow dependent on the thickness of the cobalt-iron boron. So it increases for the thicker cobalt-iron boron. So we can then go back to our finite element modeling. And from the finite element modeling, we now have the epsilon xc, and we also have the wxc. And by that, we can calculate what we would actually expect from the magnetoacoustic interaction. And that's shown here on the bottom left. So on the bottom left, so the black data points here are what we actually measured. And then the dark blue down here is what we would expect from a purely magnetoelastic interaction. The more lighter blue one are those that we expect from a purely Magneto rotation. And the red stars are actually the sum of these two contributions. Right? And what we find is that, at least in our system, we actually need both Magneto rotation and magnetoelasticity to quantitatively account for the absorption of the acoustic wave. Right? So we're quite confident that actually both contributions exist and both contributions need to be considered. And kind of like one telling thing that we really have Magneto rotation is the thickness dependency, because from a pure magnetoelastic interaction, we would not expect, at least in this thickness range, to get a thickness dependence. But because the effective magnetization is modulated with the thickness, you get a rather pronounced dependence of the Magneto rotation on thickness. Okay. So that brings me to the next topic, and that is non-reciprocity. We already looked at the amplitude non-reciprocity. We now want to go one step further and introduce also frequency non-reciprocity into magnetoacoustics. So To do so, well, one first experiment that one needs to do, I had implicitly assumed it all the time, but it has only been shown rather recently, is that actually the wavelengths of the acoustic wave corresponds to the wavelengths of the excited spin wave. So here it's been done using a synchrotron radiation XMCD measurement, where one can look at XMCD to measure the magnon, so measure the magnetic response, and use a beam to measure the electric response. So basically, one can separate the acoustic wave contributions from the magnon contributions. And what one sees here is that these two pictures look pretty much identical, right? So that indeed, the wavelengths of the acoustic wave corresponds to the wavelengths of the spin wave. That's also in agreement to our observations using phase-resolved magneto-optics. So first of all, realization, okay, we are really dealing with spin waves and not uniform mode excitation. So if we are dealing with spin waves, how can we actually improve non-reciprocity? Right, so the goal would be to go for or to generate a non-reciprocal microwave device, like a circulator or an isolator, without having to use this macroscopic, like centimeter scale devices that are typically that typically need to be used. Right? So go from something macroscopic to like a millimeter or even below chip by using acoustic surface waves instead of microwave photons. Well, thinking about non-reciprocity, well, the first thing that came to our mind was, okay, we can use the Choleshinski-Moria interaction and then rely on the non-reciprocity of the spin wave dispersion to make our device truly non-reciprocal. And that's exactly what we set out to do. So we used, again, very similar device like always. So it's a lithium niobate substrate. We put cobalt, iron, boron, platinum bilayer with some Choleshinski-Moria interaction at the interface on top of it. And we measured the acoustic transmission as a function of the external magnetic field, right at some angle. I think it was 30 degrees or so. And what we see is, well, indeed, we get a double non-reciprocity. So we get a non-reciprocity in the amplitude, which is basically going from here to here, for instance. And that's due to the helicity of the driving fields. And we also get an additional non-reciprocity in the resonance magnetic field or in the resonance frequency, vice versa, which we attribute to the shifted dispersion with the Choleshinski-Moria interaction. We again do these experiments for a range of different magnetic field orientations. And when doing so, what we find is, well, we have the spin wave non-reciprocity due to the Choleshinski-Moria interaction, and that will shift our resonance absorption compared to the case without platinum. Unfortunately, though, it also leads to enhanced damping because of spin pumping in these materials. So you get kind of like a broader line width. So what we found out here is that such a device, well, is very well suited to characterize the strength of the Choleshinski-Moria interaction, can do so with very high accuracy and sensitivity. So it's a great tool for fundamental science, but it's probably not going to cut it for any application, right? Because the non-reciprocity, you would really want to set some external magnetic field, ideally, of course, zero magnetic field, and you would want to see a clear difference in the transmission between the acoustic wave propagating in that direction and the other one. I mean, there is some non-reciprocity, but it's not enormous. It's like 4 or 5 dB, so it's not going to be good enough for any real-world applications. So we went on and looked at different ways to get spin wave non-reciprocity than using Choleshinski-Moria interaction. And another way to get highly non-reciprocal spin wave is using multi-layers. That is very well understood, that this gives non-reciprocal spin wave dispersions. We focused here on a bilayer, so it's a cobalt, iron, boron pomalloy bilayer, separated by 5 nanometers of gold, which is sufficient to suppress any exchange coupling. Right? So any coupling between these two layers will be purely dipolar from the non-uniform magnetization profile of the spin waves that we excite. Right? So one would in principle expect that there is two modes. So one is like an in-phase precession, and the other one is an out-of-phase precession of the magnetic moments in the top and the bottom layer. Before looking at the bilayer, we went back and looked at the individual layers. So this is just Cobalion Boron, in this case 5 nanometers of thickness. Can calculate the spin wave dispersion shown here, which is reciprocal of the acoustic dispersion shown here. And then, of course, if we match, if we're working at this point of the intersection, we get an absorption. It's non-reciprocal. Again, that's just the non-reciprocity due to the helicity or the elliptical driving field. Right, so that's what I already showed you in the data over here. We can also do the same thing and look at the permalloy. Okay? This is an individual layer of permalloy with some gold capping to prevent oxidation. Right? And you can immediately see, well, the symmetry looks a bit different. Right? And it's again a confirmation of what I showed you before, which is the Magneto rotation. Because in permalloy, we have very weak magnetoelasticity only. So you basically see that the driving field is dominantly coming from Magneto rotation effects. So it's basically maximum absorption around the 0-degree orientation, right? Whereas a cobalt iron boron, you need this 45-degree orientation of the magnetization to get a maximum absorption. Okay, so that's the individual layers. Now combining the two individual parts, we go to the bilayer device. And in such a bilayer device, well, we get these two different spin wave dispersions, right? So there's mode, the in-phase mode and the out-of-phase mode. So they're calculated here. So took that from this publication over here. And then, of course, you would now expect as a function of frequency to get like, well, 2 absorption peaks. Right? So let's see how it looks in the data, in the experiment. So in the experiment, we go on and carry out the experiments. And yes, indeed, we see these 2 modes, right? It's a bit more complicated here because this is now field and not frequency, because we work at a constant frequency. But as you can see on the right-hand side, it's our simulation. And again, we can capture all the details we see in the experiment using an analytical model. Okay, so this works. So we understand it. We understand that there are 2 different modes. And now we can really look how large is the non-reciprocity in such a device. So the dead end, we have to choose like an operating point parameter. So for instance, applying an external magnetic field at an angle of 45 degrees, which has a strength of about, I don't know, 45 millitesla. So that would be this light blue point, right? Or operating here on this violet point over here. And then we can invert the direction of propagation of the acoustic wave. So we go from this light blue point to that, or from that purple point to that over here. We can look at the data, and then we see the difference in absorption between these 2 points. Propagation directions is about 35 dB in both cases. The magnetoacoustic insertion loss, that means that the absorption in this point here and in this point here, where we do not want to have any absorption, is about 1 dB. It's pretty good. And well, the insertion loss of the acoustic wave device at this frequency, I think was about 7 gigahertz or something, is demonstrated experimentally that can reach about 4 dB using these materials that we use. Lower frequencies, it's lower than that. It's like 1 to 2 dB at other operating frequencies. So in total, that's I think rather promising, right? That we can get a total insertion loss of about 2 dB, non-reciprocity that easily exceeds 30 dB on a device that is potentially micrometer scale. Right? Okay, so of course that could be further optimized. So we did some calculations from different parameters that could further optimize the non-reciprocity here. Okay, that brings me to the very last part of the talk. So in the remaining 2 minutes or so, I want to give like an outlook on like ongoing work on nonlinear magnetoacoustics. So here is an experiment where we used microfocus Brion light scattering. So used an interdigital transducer, cobalt iron boron magnetic film on gallium nitride silicon substrate. And what we do is we look at using microfocus Brion light scattering with time resolution at the Magnon spectrum at a point which lies in the propagation path of the acoustic wave. Right, so a typical spectrum could look like that. So here's like the Rayleigh peak of the scattered photons, and here is our Magnon peak, for instance. And we can follow the Magnon peak at the frequency of the acoustic wave, it's a function of the external magnetic field, do that at different powers, right? And basically what one observes is at low powers, get this absorption at 7 millitesla or so, lower powers it shifts to lower magnetic fields as expected. But now the interesting part is we can, using the power of BLS, not only look at the Magnon signal at the frequency of the acoustic wave, but we can do a broadband detection, right, of any magnons at other frequencies. And if one does so in the resonant case, so setting the external magnetic field to about 6 millitesla, working here at this position, one finds, well, indeed, there is our F0, so that's the frequency of the acoustic wave. But if one actually increases the power, goes to higher power, one eventually sees the appearance of subsidiary modes, here labeled F1 and F2. So here also shown the intensity of these two modes as a function of the microwave input power. Okay. And that process can be described as a 4-magnon scattering process. Right? So basically, we use our acoustic wave, we generate 2 magnons, and those 2 magnons will then scatter under energy and momentum conservation into these 2 modes that are detected here. We can also go to lower magnetic fields, so we're below the resonance conditions with the magnetic field. This is an off-resonant case. We can still detect the non-resonant excitation of the magnon at the frequency of the acoustic wave. But now you see when we increase the power again, we again see the appearance of additional modes. And these additional modes, they can be attributed to a parallel or a parametric pumping of magnons by an acoustic wave. Right? And this is basically what I mentioned at the very beginning of the talk, that this would be a great way to actually do parametric pumping at a non-zero k vector. Right? And this is what we basically were able to show here, that there is even a direct process from an acoustic parametric pumping. So with that, I'm at the summary. So I hope that I could show you that, well, magnetoacoustic interaction has at least 2 different origins, magnetoelasticity, Magneto rotation. We can do acoustic spin wave spectroscopy using such devices, achieving potentially higher wave vectors than possible with optical means, achieving a very high accuracy and sensitivity. We can control the symmetry of this magnetoacoustic interaction by a correct choice of the surface acoustic wave mode that we're using. We can get a strong non-reciprocity in these devices because these magnetoacoustic waves are indeed chiral, so they have a handedness because we have the magnetization in there. And that can be used for miniaturized devices that are built on like a very established technological platform, right, on the surface acoustic wave platform. Finally, we're right now going into nonlinear magnetoacoustics with first results here in this archive that we have here. I want to briefly mention at the end, we have open positions for both PhD and postdocs. So if you're interested working in this field or in another field related to magnetization dynamics, please reach out to me. So with that, thank you for your attention.
Thank you. Applause to the audience. So excellent, excellent talk. Please raise your hands for the ones that would like to ask a question. Let me promote you here real quick. So I'll promote you to panelists. And if a quick question is from anonymous attendee, what is the stoichiometry of the Cobalion boron layers?
Oh, that's a good question. It's 60-40-20, but I don't actually know which one was 60, but it was iron or cobalt. I mean, I know it's in the publication, but I just forgot.
Okay, so maybe look at the publication.
Yes, but it's definitely written in there.
Okay, great. So Helen, could you go ahead and ask your question first?
Yes, thanks a lot. It was extremely interesting talk, especially for me, and I hope for cooperation. So you discuss everything from the point of view of phonons, which are linear excitations. When you are talking about nonlinear acoustic, are you thinking about nonlinear elastic excitations like solitons, or you are thinking about nonlinear magnetic excitations probed by the photons? And how far with this nonlinearity can you go?
Okay, so very good question. It's actually something right now I have a bachelor student working on that experimentally. I can tell you as much as we can go high enough in power with the surface acoustic wave devices to get non-reciprocal phononics. So we can excite, for instance, phonons at twice the frequency or half the frequency of the excitation. So that works. Here in this specific work, the processes that happen first are the magnonic instabilities, right? So they have a lower power threshold than the phononic instabilities, right? So this is why we observed it first, but it's no problem at all to go to a threshold where we get phononic instabilities as well.
And how far in frequency can you go with the surface acoustic waves? Because as far as I know, 1 gigahertz is a limit which you cannot overcome.
Okay,
can you go higher?
The answer is probably it depends. So in these standard devices that we used here, they were not optimized for a very high operation frequency. They were optimized for high bandwidths. So that's basically shown here. So this is our like frequency transmission through such a surface acoustic wave device. You can see that it is basically broadband. It's basically, it works from some 2 gigahertz or something up to 7 gigahertz in a continuous band. Okay? Which means we optimize our IDT structures to be very broadband, but that means they're not very good at exciting particularly high frequencies. We know, at least like in our own work, about 15 gigahertz is easily possible. It's been shown 20, 25 gigahertz by other groups that it's possible. The problem is you eventually have to go to vacuum to use those because you get significant losses just due to coupling to the air molecules, right? So you have to then go to vacuum conditions. If you go really above 15 gigahertz or something, it only really works in vacuum anymore. But then you're limited by lithography eventually, right? If you want to use this IDT structures, you're eventually starting to be limited by lithography. That limits you probably to frequencies substantially below 50 gigahertz in the end, using this approach, right? I mean, there's other approaches like bulk acoustic waves. You can generate surface acoustic wave from spin waves, right? Which could potentially be used to go to much higher frequencies. But we haven't successfully shown it.
Commented on that you can go to 10 gigahertz as surface acoustic waves. Okay, maybe we move to Burkhard first and then Akash. So Burkhard, you have a question?
Yeah, very, very nice talk. I have a question, Matthias, regarding what you call the Magneto Rotation effect. Is it in essence a purely geometrical effect because all you need is just a rotating anisotropy and the anisotropy is always perpendicular on the local surface, or do you need a spin-orbit coupling because you need a stronger anisotropy in that? Is it dipolar in essence?
So the origin of the anisotropy doesn't matter for the magneto rotation coupling.
Okay.
So in this case that we used, it's really just dipolar. It's the demagnetizing field, the shape anisotropy, nothing else, right?
So it's a geometric
anisotropy, and you bend your film like that, right?
Yeah, and
when you bend it, you move the normal, and that works. So you don't need even spin-orbit coupling.
Okay.
Okay, excellent. Akash, you have a question?
Thank you. Yeah, thanks for a very nice talk, Matthias. It's really interesting results. And now I have a question about the very first part. So I like your perspective about using magnetic films to map out the strains on the surface, or to map out the strains associated with the surface acoustic wave, for example. My question there is the magnetoelastic coupling function that you use, the one by Kittel, that assumes that the XYZ directions are oriented along the cubic crystal axis. And in your experiments, how important is to have your crystal orientation in a specific way, and how sensitive are you to the polycrystallinity in your film? So my question really is that is this specific crystalline interaction that Kittel writes down, is it important to have it exactly that way?
Okay, so thank you for the question, Akash. So in our case, all the experiments that I showed you have been polycrystalline films, not even textured, true polycrystalline. Okay. Which means, in my understanding, that basically when we take the Kittel approach, we have these two different magnetoelastic constants, right? The B1 and the B2, which depend on the crystalline orientation. And in a polycrystal, they're just identical, right? They're just averaged over all the different crystallites. But we can still use the epsilon XX and so on, because we have a defined axis of the propagation of the wave, right? Because we use a directed acoustic wave, we still have a very clear x-axis, which is our acoustic wave propagation, right? And then we can still use the same formalism, even though everything is polycrystalline. And of course, I mean, in a single crystal, I guess it would be more complicated. What we would get, it would kind of like introduce an additional symmetry breaking, right?
But yeah, not necessarily, because I have a suspicion that the Kittel expression is specific to cubic crystals, but it has some components which are rotational invariant, and there are only some components which are specific. So I think they might be okay, but we can discuss this later. Probably.
Okay. Yes. I'm very happy to discuss it, and maybe because we're currently also working on getting these acoustic waves in single crystals. So.
I see. Okay.
And then it will be very relevant, I think.
Right. Okay. Thanks for a nice talk.
Yeah. Thank you.
So first from Artem, can you mute yourself and ask your question? Artem? Okay, if not, he wrote it down, so I can say it. What are the temperatures that you observe the magnetoacoustic phenomena? In this case, are they room temperature or all the experiments?
Okay, so sorry, that's something I completely forgot to mention. So everything that I showed here is pure room temperature.
It's room temperature.
So this is all room temperature data so far.
Okay. And Florian, can you go ahead and ask your question? You're going to mute yourself if you like. Okay. Not sure if so. Florian Milo, you should be able to unmute yourself if you like to ask the question directly, or otherwise I read it maybe. Okay. So Florian wants to know what is your non-reciprocity ratio?
Okay, but I have to find this slide. So I guess, oh no, that's the wrong one. It's related to that one here. Okay, so the non-reciprocity ratio that you see here, just from the non-reciprocity of the magnetoelastic coupling here, I mean, you can see it. It's not very strong, right? It's maybe like 2 dB or something like that. Right? So it's not fantastic, but fundamentally, it's just the ratio of the ellipticity of the precession of the magnetization, or the polarization of your magnon, if you will, and the polarization of your driving field, which is kind of course, then again related to the polarization of your phonon. Again, right? So if you get perfect matching of these ellipticities, so in the simplest case, 2 perfect circular precessions, then it should become infinite in principle, if we were able to match that.
Okay. Excellent. Shasha, go ahead and ask your question.
Well, thank you very much for very interesting talk. I have probably the question which is follow-up of the one of this which we already asked. So for this magnetic rotation, do I understand correctly that to maximize this phenomenon, say, you just need some films with a large magnetization? That's basically what will do the job, right?
Exactly. I mean, a large anisotropy, if it comes from dipolar effects or from other effects, doesn't matter, I think.
Because I would expect that if there is large anisotropy, then probably there is a strong spin orbit coupling, and then probably magnetoelasticity will be also strong.
Yes. But exactly, it works without. So if you have a material which has a very strong magnetization, but very weak spin orbit interaction, you can still get Magneto-Rotation coupling. I mean, permalloy is one example, right? That if you hit the composition just right, the magnetoelasticity kind of like has a 0 crossing. You can make it exactly 0 in principle, but it still has a magnetization of 1 Tesla, right? So you can still get a substantial Magneto-Rotation out of it.
Right. Thank you.
Great. Laura, would you like to ask a question? If you want to unmute yourself, yeah.
Sorry.
I might just remove my mask temporarily. Hello, nice to meet you. Thank you very much for all these amazing results. Yes, I'll just read out loud the question I wrote up. Since the very beginning of your papers, you kind of systematically ignore this epsilon ZZ component of the Rayleigh wave, which indeed doesn't lead to any torque when the magnetization is in the plane. It does give a torque when it's anywhere between in the plane and out of the plane. And so I was wondering whether you checked that it doesn't have any effect on the other energies you put in. Because, and yeah, I'm kind of wondering why you kind of completely ignore it in your modeling. It does give a zero torque in like the usual expression, but since you added in lots of other ingredients, yeah, thanks a lot.
Okay. So thank you. So indeed, we typically we typically drop it because the torques that we get there are in the end then in 2-second order. So our model is only like first order of the magnetization excitation in the end, which means it's kind of like goes one step beyond the Kittel original, which was 0th order, basically, so to speak, because it was only the MZ component. We take like the transversal components, but we don't take like the change of the MZ component in the end with like deconing. But that's something you definitely consider that, I guess, in your experiments when you do switching experiments, when you have very large magnetization excitation, then it becomes very important, right? Obviously, you cannot ignore it. And I think also when we now move towards the nonlinear stuff, we probably will need to include it. It's just that, we wanted to keep the model as simple as possible while still getting a very good agreement to the data. So we didn't need to include it, I think. You saw that we got a very good match, but I completely agree that it is there, right?
Yeah, like for this term you just put up, definitely, but like for the DMI part, for instance, there's no particular torque that comes up. I haven't done the math for this part of the energy, so I was just wondering.
Yeah, so the DMI, we only consider the DMI insofar as that it changes the spin wave dispersion. Right?
You didn't include it in your magnetoacoustic dynamic?
No, not at all. So okay. In our model here, the only part where the DMI enters is in the pole susceptibility over here, right? So it's basically just changing the resonance condition.
Right, but you could also derive the corresponding effective field, I guess. I haven't done it. Since it works with all the other energy terms, yes. I'm just wondering whether epsilon XX and ZZ would give an interesting torque, effective magnetoacoustic torque by the DMI. But
I cannot really imagine that it will do that right now, because as far as I see it from the symmetry, the DMI only shifts basically like some in-plane things, like in-plane dispersion. So I don't think that it will, but I'm not sure.
Okay, no,
it's very easy
a good
to
argument.
test. At least in the mathematical model, the epsilon ZZ is just set to 0. It's even included in the model in the code. It's just always set it to 0. We can do that and check it, but I cannot tell you right now if it has any effect. But my guess would be that it does not have an effect.
Thank you so much.
Thank you. Vincent, I think we have one last question from Vincent, if you'd like to ask a question.
Yeah, thank you. Actually, I have 2 questions. First, let me thank you for the very nice talk. Actually, the question, let's say, concentrate on the second part. Can you go, please, Mathias, to the slide number 17? Yeah, thanks. The first question, I was wondering at one point, you said that some of the peaks you observe in the blue curve could correspond to the bulk acoustic wave that, let's say, is not acting on the magnetic thin films. But is it possible that you observe also some harmonics in your system with your delay line?
So did I hear? So you're asking about harmonics, which you mean? So do you mean by harmonics that we excite the IDT? So here at 3 or 4 gigahertz, and that these are actually at a different frequency? Is that what you mean?
Yeah, I was wondering if it was possible that you excite a Rayleigh wave, for instance, at twice the frequency with the harmonic. And is it possible to observe this in your experiment?
Okay, so the answer is, I think it's not happening here, but in principle, we can observe it. We would not observe it in this data because here we use the vector network analyzer and it's only even sensitive, right? We don't measure the microwave power, but we measure it with a vector network analyzer. So we only see the microwave frequency components at exactly the frequency that we send into the system. So in this experiment, we would be completely blind to these things. Okay. But in the BLS, we're not, right? So in the BLS spectroscopy, we could see it. And here, I mean, you see the insertion loss that we have here in this particular system. I mean, it's minus 60, minus 90 dB. There is just no way we have enough power to excite anything nonlinear in the acoustics here. It's just because the IDT design was not optimized to get a low insertion loss. Right? It's 60 dB insertion loss.
Okay, I get it. Okay, thanks. And the second quick question, you said that the possible shear horizontal unknown wave, because you said shear horizontal, is it possible to have like a shear vertical wave?
It's totally possible, but it would have a different symmetry, right? So if this would be a shear vertical wave, the symmetry here would not be like that. I think the symmetry would be, we would not see these spots up here and down here. You would only see the absorption at 0 degree. Right? Okay,
but more or less at the same velocity.
Yeah, I mean, the velocity here, because it's an unknown mode in the sense that if we try to simulate it with COMSOL, we're not able to reproduce it. So I don't know anything about the expected velocity.
Okay.
In any reasonable model that we put into the finite element modeling, it doesn't exist. So we have truly no idea where it's coming from. But we know that it has a symmetry of a shear horizontal wave and not a shear vertical.
Okay, great. Thank you.
Perfect. Okay, I think with this, that concludes for today. I'm going to stop the streaming and thank once again, right now,